Hello everyone, and welcome to another lecture in differential equations. Last time we finished up our discussion of how to find the complementary solutions, and we considered all of the possible cases. That we considered all of the cases when things go wrong. So as far as finding the complementary solution, to a differential equation, specifically a linear differential equation with constant coefficients. We've covered everything. There shouldn't be anything that we come across that we haven't learned how to deal with. Now, you remember the reason that we were so interested in the complementary solution is that if we have a linear differential equation with constant coefficients, our strategy is to find a particular solution, any solution, and add to it the general complementary solution. And the sum of those two things will give us the general solution of the original linear differential equation with constant coefficients. We know how to find the complementary solutions. So what we're going to talk about today is how to find particular solutions. And you know, there's no one method that works for everything. So there are a couple of methods that we're going to look at. This is called the method of undetermined coefficients. And somewhat with a little humor, I write, and they shall reproduce, each one according to its kind. Where have I heard that before? I think I read it somewhere. Okay. But this is actually an apt quote to put us in the right frame of mind to embark on the journey that we're about to embark on. Think about this. If you have sine of x and you compute the derivative of sine of x, what do you get? Well, you get cosine of x. And if you have cosine of x and you compute the derivative of cosine of x, what do you get? Well, you get negative sine of x. Okay, and if you compute the derivative of negative sine of x, what do you get? Negative cosine of x. And if you compute the derivative of negative cosine of x, what do you get? Sine of x, etc., etc. If we take sine of x and or cosine of x, and we keep computing the derivatives of those things, we get more sine of x's and more cosine of x's. Now, think about this from a different perspective. Is there any function that we know of, other than sine x or cosine of x, that we can compute the derivative of to get sine x or cosine of x? If you want to compute the derivative of a function and get sine of x and cosine of x, that function has to contain sine of x and cosine of x. And if you have a function that consists of a linear combination of sine of x and cosine of x, and you compute the derivative of that function, what are you going to get? More sine of x's and more cosine of x's. Exponential functions are the same way. If you compute the derivative of e to the x, what do you get? You get e to the x. And if you compute the derivative of e to the x again, what do you get? Well, you get e to the x. Is there any function other than e to the x that we can compute the derivative of and get e to the x? If we want to get e to the x by computing derivatives, we have to start with e to the x. And what about a polynomial? What do you get if you compute the derivative of a polynomial? Like this one. We'll say 2x cubed plus 3x squared minus 6x plus 5. That's our polynomial. And we compute the derivative of that polynomial. What do we get? Let's say 6x squared plus 6x minus 6. That's it. Well, the point here is that we started with a polynomial, and we computed the derivative of that polynomial, and what did we get? Sines and cosines? No. We computed the derivative of a polynomial, and we got a polynomial. Now let's look at it from the opposite perspective. Are there any functions other than polynomials that we can compute the derivative of and get a polynomial? No. If you want to get a polynomial by computing the derivative of some function, that function better be a polynomial. If you want to get sine of x and cosine of x by computing the derivative of some function, that function better contain sine of x and cosine of x. And if you want e to the x by computing the derivative of some function, that function better contain e to the x. Now, let me get a little bit more explicit, but you see where we're going. They shall reproduce each one according to its kind. Sine of x and cosine of x, you compute the derivative of them, you get little sines of x and little cosines of x. And if you compute the derivative of mama and papa e to the x, you get little e to the x's. And if you compute the derivatives of polynomials, you get little bitty polynomials. And this is true, and this is the whole point of the method of undetermined coefficients. Exponential functions, sines and cosines, and polynomials are fairly unique in the sense that the only way that you can get them by computing derivatives is to start out with the same kinds of functions. If you want sines and cosines by computing derivatives, you got to start out with sines and cosines. If you want exponentials by computing the derivative of a function, that function better be an exponential. If you want a polynomial by computing the derivative of some function, that function better be a polynomial. Now, suppose I have e to the 2x. It's an exponential. Am I going to get this function by computing the derivative of e to the x? No. If I want e to the 2x, my function better contain e to the 2x. If I want e to the 5x, the function that I compute the derivative of to get e to the 5x better contain e to the 5x. I'm not going to get e to the 5x by computing the derivative of e to the x. That's not going to happen. The same is true of sines and cosines. Let's say that we have cosine of 3x. Am I going to get this function by computing the derivative of sine of x and or cosine of x? No. If I compute the derivative of sine of x and or cosine of x, I'm just going to get more sines of x's and more cosines of x's. If I want to get cosine of 3x by computing the derivative of some function, what does that function have to look like? Isn't it going to have to be a linear combination of sine of 3x and cosine of 3x? The argument, 3x, is going to have to be the same in all of the functions. So that's sort of a preview of the principle that we're going to be working on. Oh, I sure hope I spelled this right. There, did that fit on the screen? I guess it did. This is our f of x. Did that make it cosine? Okay. The right-hand side of our equation is a linear combination of sine x and cosine of x. So what we assume is that our particular solution is also a linear combination of sine of x and cosine of x. And we compute all of the derivatives of y that appear in the equation. And we plug these into the original equation. Now, if we compute y prime, we're going to get sine of x and cosine of x. If we compute y double prime, we're going to get sine x and cosine of x and so forth. So we take all of these things and plug them into this equation, and we're going to get sines of x's and cosines of x's. So we'll combine terms. Combine like terms. And then we solve for C1 and C2. You see, we're convinced that since the right-hand side of this equation is a linear combination of sines and cosines, we're convinced that our particular solution also has to be some linear combination of sines and cosines. So we'll say C1 sine of x plus C2 cosine of x. And we compute y prime, y double prime, and so forth, and plug all of these things into the original equation and combine like terms, and then just solve for C1 and C2. We can do that. So that's what we do if we have sines and cosines. Now, let me ask a question. Suppose my f of x just looks like this. Then what do I do? Well, you know, it is possible to get sine of x by computing the derivative of cosine of x. It is possible, isn't it? So you know what? I'm going to start out assuming that my particular solution is a linear combination of both sines and cosines. Oh, but Dr. Rossi, suppose that the original solution only has sine and no cosine. That's okay. If it turns out that my particular solution is just some constant times sine of x, and there's no cosine term here, you know what? When I compute the derivative of this thing and plug it into the equation for y prime, y double prime, and all of that, when I compute all of these derivatives and plug them into the original equation, and I solve for C1 and C2, if there really is no cosine term here in my particular solution, guess what? C2 is going to turn out to be 0. Now let's look at another scenario. Let's say that my f of x looks like this. I'm going to assume that my particular solution looks like some constant times e to the 2x. And then I'll compute y prime, y double prime, the nth derivative of y, and plug these into the original equation. I'll combine like terms, and I'll solve for C1. And what about a polynomial? What about a polynomial? No. Hold on a minute. Five x squared plus 6x minus 3 The right-hand side of this equation is a polynomial. So what am I going to assume? That my particular solution is sine and cosine? No, of course not. To get a polynomial, we compute the derivatives of polynomials. And since this is a second-degree polynomial, I'll assume that my particular solution is also second degree. Now, there is a monster in the closet that I haven't let out yet. I will when the time is right. In the meantime, I will keep the monster in the closet so you don't have to worry about that case. But these essentially are the three scenarios that will prompt us to use the method of undetermined coefficients. And see, A, B, and C are those undetermined coefficients that we will solve for and find using some fancy detective work. Now, enough yakking. Let's get down to some examples. Okay, the right-hand side, f of x, is some linear combination of sines of x's and cosines of x's. So I'm going to use method of undetermined coefficients. I'm going to assume my particular solution is c1 sine of x plus c2 cosine of x. And this is a second degree or a second order differential equation. So I need to compute y prime and y double prime. There's y prime. Now I need y double prime. Okay, negative c1 sine of x minus c2 cosine of x. Looks good. y double prime. Okay. So that's going to be negative c1 sine of x minus c2 cosine of x okay, minus 4y c1 sine of x plus c2 cosine of x So there we have it. Y double prime minus 4y. Now, let's see. What do we get? We're supposed to get 5 sine of x. Let's collect like terms. We have negative c1 sine of x minus 4c1 sine of x. Okay. So that's going to be negative 5c1 sine of x. And we have negative c2 cosine of x minus 4 c2 cosine of x. So that's negative 5 c2 cosine of x. And that's supposed to be equal to 5 sine of x. On each side of the equation, we have a linear combination of sine of x and cosine of x. So let's see. Compare coefficients of sine of x. Negative 5c1 equals 5. And that means that c1 is equal to negative 1. Now, what about comparing the coefficients of cosine of x? I don't see cosine of x over here. You know why I don't see cosine of x over here? Because its coefficient is 0. Now, when I compare the coefficients, I have something to compare. So I have negative 5c2 equals 0, and that means that c2 equals 0. And this is a great example because it shows us that we have nothing to worry about assuming that the solution is a linear combination of sines and cosines. Oh, but what if there is no cosine? See, we assumed particular solution was equal to 5 sine of x plus, no I didn't. I assumed the particular solution was c1 sine of x plus c2 cosine of x. And we might be wondering, oh, but there's only a sine of x here. There's no cosine of x. What do we do? Well, if the particular solution really doesn't have a cosine of x term, then its coefficient is going to turn out to be 0. The problem solves itself. So here's what our particular solution turned out to be. That wasn't half bad, was it? As a matter of fact, I kind of enjoyed it. Now, before we go on to other examples, let's just tie this in with the complementary equation stuff that we've been doing. Let's see, y double prime minus 4y equals 5 sine of x. Now, if we were starting from scratch, the first thing we'd do, we'd find the complementary solution. The only reason that we found the particular solution in this case is because we were illustrating the technique of undetermined coefficients. But there's actually a good reason why we should find the complementary solution first. First thing to do, we'll write it using operator notation. Second derivative of y minus 4y is 0. And then I'll factor out the y's. And this yields as a coefficient of y the polynomial phi of d. And that's important because my next step is to write the auxiliary equation and to solve that auxiliary equation. So my auxiliary equation is the same polynomial in terms of m. So here's phi of m. And I factor this son of a gun. And I'll write y sub c there. That's our complementary solution. To get the general solution, we take any particular solution and add to it the complementary solution. This thing right here. Now, what did our particular solution turn out to be? Wasn't it -1? I think it was. I hope it was. Yeah. The particular solution was negative sine of x. There's our general solution. The sum of a particular solution, and there are infinitely many of those, but all we need is one particular solution, plus the general complementary solution. That gives us the general solution to the differential equation y double prime minus 4y prime equals 5 sine of x. Well, this is the same complementary equation that we solved in the previous example. So we have our complementary solution. I'm looking at the right-hand side of this equation. The right-hand side of this equation is a polynomial of degree 2. Okay, this is what our particular solution looks like. We just have to find the coefficients A, B, and C. Holy moly, what was that polynomial? Negative 12x squared minus 20x plus 30. Okay. So we have y double prime minus 4y. And what is y? It's this thing. And all of that should equal negative 12x squared minus 20x plus 30. And I guess I'm going to collect like terms in the sense that I'm going to get all the constants together in one term. I'm going to get all the x terms together in one term. I'm going to get all the x squared terms together in one term. So let's see. We only have one x squared term, negative 4ax squared. Okay, now I only have one x term, negative 4bx. Oh, this is easy. Wow. Now, constant terms, I have 2a minus 4c. And that's equal to our polynomial 12x squared minus 20x plus 30. And we compare coefficients. It is a fact that two polynomials are equal if and only if they have exactly the same coefficients for each term. So, negative 4a is equal to negative 12. So that means that a is equal to 3. Now let's look at the coefficients of x. 4b and negative 20. They have to be the same because they're both coefficients of x. So negative 4b is equal to negative 20. And that means b is equal to 5. And the constant term, well, this will take a little bit more detective work, but not much. What do we have here? 2a minus 4c equals 30. But we know what a is. A is 3. So c is equal to 6. Okay. Cool. So we had ax squared plus by plus c, and a turned out to be 3. B turned out to be 5. C turned out to be, B turned out to be 5x. I beg your pardon. C turned out to be 6. Our general solution, it's the sum of any particular solution plus the complementary solution. So our particular solution is 3x squared plus 5x plus 6. And the complementary solution, C1 e to the negative 2x, C2 e to the 2x. It's looking good. Looking good, good, good. Now, there are a few things that we have to watch out for. And this example will illustrate one of them. By the way, this example will also illustrate why it is that we always want to find the complementary solution first. That's our complementary solution. And getting the complementary solution before we look for the particular solution is going to be helpful in this case. We do exactly what we're supposed to do. We're doing this exactly the way we were supposed to do it. we look at the right-hand side of the original equation and we say, okay, that's an exponential. You only get exponentials, you only get baby exponentials from mom and pop exponentials. So the original solution, the particular solution, has to be some constant times e to the 2x. Holy moly. I saved myself some aggravation. I saved myself about 5 or 10 minutes of computation, only to find out that I didn't get what I thought I should get. Now, I was right to conjecture that my particular solution is some constant times e to the 2x. I was also right to be thinking in the back of my mind, some constant times e to the 2x. Haven't we seen that somewhere before? And I look up, and here is some constant times e to the 2x is part of the complementary solution. C2, or some constant times e to the 2x, is one of the two independent solutions that form the complementary solution. Well, if this is one of the solutions to the complementary equation, that means that if I take some constant times e to the 2x and plug it in for y and y double prime, I'm going to get y double prime minus 4y equals 0. So, this isn't going to work. And let me just if we compute y double prime and plug particular solution in y double prime into y double prime minus 4y, what's this thing here? Just a very big comma. There. But if this is my proposed particular solution, and I compute y double prime, and I plug this thing in y double prime into that expression, I'm not going to get 6e to the 2x. I'm going to get 0. So this is not going to be my particular solution. It can't be, because it's part of the complementary solution. See, yeah, this is part of my complementary solution. It can't be my particular solution too, because the independent complementary solutions give us 0 when we plug in for y and y double prime. So we can't take this same thing and plug in for y and y double prime and get 6e to the 2x. It's not going to happen. Oh, crud. Well, I'll tell you how we handle this. It turns out that we've used the same fix-it for another problem that popped up with the complementary solution. Remember what we did when we had a double root in the complementary equation? Let's say that m equal 3 was a double root. Well, our first independent solution would have been c1 e to the 3x. But then our second solution can't be c2 e to the 3x, because these are really the same solution. And we said, no, that's not going to work. So what did we do to this thing to turn it into a solution? Didn't we take it and multiply by x, and all of a sudden, this became the second independent solution? Well, you know what? If we have this situation where our proposed particular solution is actually one of the independent solutions, we get the particular solution by multiplying by x. It actually works. So we say particular solution is c1, but not e to the 2x, but rather c1x e to the 2x. And believe it or not, that's going to fix everything. I'll prove it to you. Now we'll compute y prime and y double prime. Let's see, what do we get when we compute y double prime? We get c1, and then, isn't this a product? We got to use the product rule. So we get first times derivative of the second plus second times derivative of the first. And, oh, what is that? That's going to be C1, and I'll write it down here. C1 e to the 2x plus 2C1x e to the 2x so that's my first derivative. I need the second derivative. Okay. Derivative of this is derivative of this is 2C1 e to the 2x. And then we do derivative of this thing. We have 2C1 and x e to the 2x is a product. We have to use the product rule, and we know how to do that because we did it up here. We're going to get x times 2e to the 2x plus e to the 2x times 1 okay. We have 2C1 e to the 2x plus 2C1 e to the 2x is 4C1 e to the 2x. And then we have 2C1 times 2 is 4C1 x e to the 2x. Okay, y double prime. That's going to be 4C1 e to the 2x plus 4C1 x e to the 2x so this is y double prime minus 4y. And here's y, just C1 x e to the 2x. And now we're going to combine terms. So we have 4c1x e to the 2x minus 4c1x e to the 2x. That's 0. All we have left is this thing. And we compare coefficients. So there's our particular solution. By the way, if we hadn't found the complementary solution first, then when we proposed to have the particular solution equal c1 e to the 2x, we would have seen nothing wrong with that. We would have plugged that into the equation, we would have gotten 0, and we would have gone, how did that happen? But since we computed the complementary equation or the complementary solution first, when we proposed to have the particular solution be c1 e to the 2x, we stopped and said, wait a minute, that's part of our complementary solution. Something's wrong there. So that's why we always want to compute the complementary solution first. Now there's one other thing that I should talk to you about. It's It's not all that complicated, but we might not think about it until we run into that situation. Here's what we need to talk about. The situation where y is actually missing from the equation. It looks harmless enough. The right-hand side is a polynomial. And when we go to find the particular solution, which we don't do until we have the complementary solution, we'll assume we have the complementary solution already. In our equation, we have a second-degree polynomial. So we surmise that the particular solution is also a second-degree polynomial. And we compute the derivatives. And we plug these in to the original equation. And here's what we get. We get 3y double prime, so that's 3 times 2a. And we get 2y prime, which is 2ax plus b. And this is going to equal 6x squared plus 3x plus 4. And we simplify. So we have an x term here, and our constant term is 6a plus 2b. And we compare coefficients. Well, we compare constant to constant. And we compare first degree term to first degree term. There's no second degree term over here. There's a second degree term here, but our proposed solution, ax squared plus bx plus c, didn't give us a second degree term when we plugged in. Ooh, what went wrong? Oh my goodness. See, what did I have? Oh my goodness. I'm sorry, I don't remember the original equation. Oh crud. Oh well, we had something y double prime plus something y prime equals 6x squared plus 3x plus whatever that was, 5 maybe. The problem came down to the fact that there was no y term. Yeah, let's see. We said y equals ax squared plus bx plus c. Y prime is 2ax plus b. And y double prime is 2a. But there's no y prime, there's no y term here. There's just y prime and y double prime. So we take y prime and plug it in here. We take y double prime, and let me back up a little bit. We take y prime, which does not have an x squared term, and we plug it in here. And we take y double prime, which doesn't have an x squared term, and we plug it in here. Well, neither of these two things, when we plug them into the equation, are going to give us an x squared. We were counting on the original function, y sub p to give us our x squared. But see, in our equation, there is no y term here. And so we can't plug y in anywhere into this equation, and we're not going to get an x squared term on the left-hand side. If we're surmising that the particular solution is a polynomial, then the derivative is going to be a polynomial of degree 1 less. Now, I surmised that my solution was going to be a second-degree polynomial, but when I compute the derivative, that gives me a first-degree polynomial, and that's not going to give me x squared. What should I have done differently? Was that what it was? Yeah, when I saw this, I should have said, there's no y term here. So whatever y prime is going to have to give me my 3x squared. So I'm going to say my particular solution is going to be ax cubed plus bx squared plus cx plus d. And then when I compute the first derivative, I'm going to get 3ax squared plus 2bx plus c. And this will give me my x squared term. So when we're doing method of undetermined coefficients with a polynomial on the right side, and we don't have a y term here, the term of lowest order on the left is y prime. Instead of saying, aha, this is a second degree polynomial, so my particular solution will be a second degree polynomial, I'm going to say, this is a second degree polynomial, but since I don't have a y term over here, the derivative of my particular solution will have to be a second degree polynomial. And my particular solution will actually have to be a third degree polynomial. So I wanted to let that monster out of the closet because you might see it in the homework exercises. Oh, and if you do, well, let's see. You might see it in the homework exercises. You won't see it in the homework exercises unless I actually write down the homework. Okay, there we go. Method of undetermined coefficients. And page 197, they let some of the monsters out of the closet, but we know how to deal with them now. So work hard on these. Enjoy working hard. And after we get these down, we'll look at another method for getting particular solutions. And it's the method we use when the right-hand side of the equation doesn't consist solely of sines, cosines, exponentials, and polynomials. But work on these for now. Enjoy working on them. Be safe. Exercise soundness of mind in all that we do, so that in a few weeks we can be back in school with smiles on our faces and none the worse for this temporary detour. But we're going to have a good semester, and we're going to do everything that we're supposed to do in this semester. It's going to be a successful semester. Enjoy this, work hard, and in a couple of days I'll give you something else to work hard on.